Unit 1A, Lesson 3. In this lesson, we're going to talk about some different properties dealing with exponents, and we're going to use those properties in order to simplify expressions. Here are the basic properties of exponents that we're going to go through. For all of these examples, we're going to let a and b represent real numbers, and m and n represent integers. So the first property we have is the product of powers. So if we are multiplying two quantities that have the same base, in this case a, then we can combine that into 1 by adding those exponents together. Okay, we can see an example to the right. If we have 3 squared times 3 to the 5th, our base of 3 is the same, so we add those two exponents together, which would simplify down to 3 to the 7th power. Next one is a power of a power. So we have some quantity a raised to a power, and then that whole quantity raised to another power. This time we multiply those two values together. So we would take m times n to write that as a single quantity. Next we have the power of a product. So if we have inside parentheses two factors being multiplied, that whole quantity raised to some power, then that power gets applied to both of those factors inside the parentheses. Next we have the negative exponent property. We also refer to this sometimes as the reciprocal property. When dealing with exponents, we always want to write them as positive values, not negative. So if we have a raised to the negative n power, to make that positive, we essentially take the reciprocal and write 1 over a to the m. Next we have the zero exponent property, which essentially says any value raised to the 0 power is going to be equal to 1, as long as that value is not 0. Next we have the quotient of powers. Similar to the product of powers, if we have a to the m divided by a to the n, as long as this base a is the same, when we're dividing, now we just subtract those exponents. And then the last one, we have a power of a quotient. If inside parentheses we have a fraction raised to some power, we apply that power to both the numerator and denominator of that fraction. Now we're going to go through a few examples applying those various properties we just went through. Okay, so the first one, we have x to the 4th times x to the 7th. This is going to be that first property we talked about, the product of powers. If our base is the same, which it is in this case, x, then to write this as 1, we just have to add our exponents together. So this would simplify down to x to the 11th power. The next example, number 2, it's a little more complicated. There's a lot going on. We're going to have to use a few different properties. Okay, there's a couple different ways you could approach this problem, so I'm going to go through one way you could simplify this problem. And then after that, I want you to think about if there's another way you could simplify it to get the same answer. Okay, so we have a to the 7th times b to the 3rd, that divided by a to the 4th times b squared, that whole quantity raised to the 3rd power. So what I'm going to do is simplify what's inside the parentheses as much as possible. And to do that, I'm looking at my factors that have the same base. So I see I have a base of a in the numerator and denominator. So I have a property that tells me if we're dividing those factors, then we subtract the exponents. So if I want to write this as one factor, I would take a and then subtract the exponents, so it would be 7 minus 4, which leaves me with a cubed. If we use the same idea with our factor b, we have b cubed divided by b squared. We just write that as one factor, so we'd take 3 minus 2 to get b to the 1st power. Technically, if you have b to the 1st power, we don't have to write that exponent of 1 there. And then that whole quantity is raised to the 3rd power still. Now we have to use the power to a power property. This power of 3 gets applied to both factors inside the parentheses, and we multiply those exponents, those powers together. So 3 times 3, we would get a to the 9th. And then 1 times 3 is 3, so we'd have b cubed. So now I want you to think about if there's another approach you could take to get the same simplified answer. Now the third example, we have x cubed times y to the 4th, all that divided by x to the 9th times y to the 6th. So this problem we're going to use same properties we used in the previous problem. I have my base x, which is the same, so I subtract the exponents. So I get x, and then 3 minus 9 would give me -6. Then do the same thing with my base y. 4 minus 6 would get me -2. Now we have to use that negative exponent property. We always want to write our expressions, our factors, our bases with exponents, powers that are positive. So if I want to make this positive, I have to move that to the denominator of the fraction. So if I move that to the denominator, I would get x to the 6th. If I do the same thing with my y value, I would get y squared. And then in the numerator, we can't just leave that blank, and it's not a value of 0, because if we had 0 divided by some quantity, that would be 0. So what we have left in the numerator is just a factor of 1. And we could have that factor of 1 written out in the previous portion before we simplified. 1 times anything is itself, so that factor of 1 is there. We have to account for it. A question some of you may have is, how do you know when you're done? How do you know when the expression is simplified as much as possible? There's two main things you have to be aware of or look out for. The first one, make sure you have no negative exponents on any of your expressions. If you have a negative exponent somewhere, then the expression is not simplified. The other thing you have to be concerned with is making sure you combine any bases together that are the same. Just like in the last problem, we had a base of x in the numerator and denominator. We want to make sure at some point in our simplified expression that we are going to write that as one base. The last thing we're going to go through in this lesson is a proof showing why the zero exponent property works. That's why any value, any real number raised to the 0 power is going to be equal to 1. So in the end, we're going to show why a raised to the 0 power, some real number or expression raised to 0 power, is always going to be equal to 1. And when going through a proof, we have to use variables in our proof. We can't use actual numbers. If we use actual numbers, we're just showing that only that case is true, that proof for that exact number is true. We use variables in our proof representing every real number to show that it's always going to be true for any real number we would use. So to show this proof, I'm going to start with a to the n divided by a to the n. A just represents some real number, n represents some integer. So if we have a to the n divided by a to the n, when we have something divided by itself, anything divided by itself, we know is equal to 1. Okay, that's basic math. Anything divided by itself always is going to be equal to 1. We also can apply one of the properties we just learned in this lesson. If our base a is the same and we're dividing, then we subtract our exponents. So we would get a to the n minus n, subtracting those exponent powers. Well, if we simplify this one more step, n minus n, anything minus itself is going to be 0. So now we get a to the 0. So we just showed a to the 0 is always going to be equal to 1. Any real number or expression raised to the 0 power will be equal to 1. In this lesson, we went through many different properties that we can apply to exponents. Before class, there's something else I want you to consider and look at. For the last 4 properties, the negative exponent, zero exponent, quotient of powers, and power of a quotient, there is a condition that is always going to be true, or that has to be met. For the negative exponent, it tells us that a cannot be equal to 0. For the zero exponent, a cannot be equal to 0. Quotient of powers, a cannot be equal to 0. And the last one, power of a quotient, we have the condition b cannot be equal to 0. Okay, so a and b represent real numbers, and we have this condition where that real number cannot be 0. I want you to think about why that condition has to be there.